NEC 705.15 requires that a listed transfer switch be used to connect two or more sources to a permanently installed electrical system. NEC 705.16b requires that each source of a transfer switch be provided with protection from overcurrent and ground faults. NEC 215.12 requires that the service disconnect be located outside a dwelling at a readily accessible location. Based on the NEC requirements, a transfer switch must have overcurrent protection for each source. However, the location of this protection depends on whether the transfer switch is considered a service disconnect. If the transfer switch is considered a service disconnect, the overcurrent protection must be installed ahead of it. This is because a service disconnect is the first point of overcurrent protection for the entire electrical system. If the transfer switch is not considered a service disconnect, the overcurrent protection for the sources can be installed either ahead of or after the transfer switch. However, the overcurrent protection must still be readily accessible. The different answers from inspectors may be due to the interpretation of whether the transfer switch is considered a service disconnect. Some inspectors may believe that the transfer switch is a service disconnect because it has the ability to isolate the electrical system from both sources. Others may believe that the transfer switch is not a service disconnect because it is not located outside the dwelling. To avoid potential disputes with inspectors, it is recommended to install overcurrent protection ahead of the transfer switch. This ensures that the transfer switch meets the NEC requirement for overcurrent protection for each source, and it also meets the requirement for a service disconnect if the transfer switch is considered as such. Let's delve deeper into the NEC requirements concerning transfer switches and overcurrent protection, focusing on a residential installation scenario. The National Electrical Code, or NEC, serves as a benchmark for safe electrical design, installation, and inspection to protect people and property from electrical hazards. Understanding its nuances is crucial for any electrical installation, especially when dealing with multiple power sources like a generator and the utility grid. Firstly, NEC 705.15 mandates the use of a listed transfer switch. The term listed refers to equipment that has been evaluated by a recognized testing laboratory, such as Underwriters Laboratories UL, and found to meet specific safety standards. This listing ensures the transfer switch is suitable for its intended purpose and minimizes the risk of electrical hazards. Secondly, NEC 705.16b is very specific about overcurrent and ground fault protection. It stipulates that each power source connected to the transfer switch, whether it's the utility grid or the generator, must have its own overcurrent protection. This protection is essential to prevent damage to equipment and wiring in the event of a fault, such as a short circuit or ground fault. The overcurrent protection device, typically a circuit breaker or fuse, is designed to interrupt the flow of electricity when the current exceeds a safe level. And thirdly, NEC 215.12 dictates that the service disconnect must be located outside a dwelling at a readily accessible location. The service disconnect is the main point of cutoff for electrical power entering the building. Its location is critical for emergency situations, allowing firefighters or other first responders to quickly de-energize the electrical system. Now let's consider the interpretation of these requirements. The key question is whether the transfer switch is considered a service disconnect. This determination affects the placement of the overcurrent protection devices. If the transfer switch is deemed a service disconnect, it must have overcurrent protection installed ahead of it. This means the overcurrent protection device is located on the supply side of the transfer switch, closer to the power source, like the meter. The reasoning behind this is that the service disconnect serves as the primary overcurrent protection for the entire electrical system. It is the first line of defense against electrical faults. If the transfer switch is not considered a service disconnect, the overcurrent protection for each source can be located either ahead of or after the transfer switch. However, it's important to note that the overcurrent protection must still be readily accessible. This means it should be easily reached for inspection, maintenance, or resetting in the event of a trip. The differing opinions among inspectors often stem from varying interpretations of whether the transfer switch functions as a service disconnect. Some inspectors may argue that because the transfer switch can isolate the electrical system from both the utility grid and the generator, it effectively acts as a service disconnect. Therefore, they would require overcurrent protection ahead of the transfer switch. Others may contend that because the transfer switch is not located outside the dwelling, as required for a service disconnect, it should not be considered as such. In this case, they might allow the overcurrent protection to be located after the transfer switch. To mitigate potential disagreements with inspectors and ensure compliance with the NEC, it's generally recommended to install overcurrent protection ahead of the transfer switch. This approach satisfies the requirement for overcurrent protection for each source and also addresses the requirements for service disconnect if the transfer switch is interpreted as such. When selecting overcurrent protection devices, it's crucial to choose the appropriate ampacity and interrupting rating. The ampacity refers to the amount of current a device can safely carry continuously, while the interrupting rating indicates the maximum fault current the device can safely interrupt. The ampacity should be matched to the circuit's load requirements, and the interrupting rating should be sufficient to handle the available fault current at the installation location. Let's discuss some specific NEC articles that provide further guidance on overcurrent protection. NEC 240 covers the general requirements for overcurrent protection, including the types of devices permitted, their application, and their installation. NEC 240.4 addresses the protection of conductors, specifying that conductors must be protected against overcurrent in accordance with their ampacities. This means the overcurrent protection device should be sized no larger than the conductor's ampacity unless certain exceptions apply. NEC 240.21 provides rules for locating overcurrent protection devices, specifying the maximum length of conductors permitted without overcurrent protection at their supply point. This is important for ensuring that conductors are adequately protected against faults throughout the electrical system. NEC 445 covers generators, including requirements for overcurrent protection. It specifies that generators must have overcurrent protection devices to protect them from overload and short-circuit conditions. NEC 700 addresses emergency systems, including requirements for overcurrent protection for emergency circuits. These circuits are designed to provide power to essential loads during power outages, such as lighting, fire alarms, and life support equipment. In a residential installation, the overcurrent protection head of the transfer switch would typically consist of a circuit breaker or fuse installed in the main service panel or a separate disconnect enclosure. The size of the overcurrent protection device would depend on the ampacity of the service conductors and the load requirements of the electrical system. The generator would also have its own overcurrent protection, typically a circuit breaker, installed in the generator's control panel. This breaker would protect the generator from overload and short-circuit conditions. When installing a transfer switch, it's important to follow the manufacturer's instructions carefully. The instructions will provide detailed information on the proper wiring and installation procedures, as well as any specific requirements for overcurrent protection. It's also advisable to consult with a qualified electrician to ensure that the installation complies with all applicable codes and regulations. A qualified electrician can assess the specific requirements of the installation and recommend the appropriate overcurrent protection devices and wiring methods. They can also perform the necessary inspections and tests to ensure that the installation is safe and reliable. Now, let's address some common questions that arise regarding transfer switches and overcurrent protection. Can I use a single overcurrent protection device to protect both the utility grid and the generator? No, each source must have its own overcurrent protection device. This is because the utility grid and the generator operate independently and may have different voltage and current characteristics. Can I use a fuse instead of a circuit breaker for overcurrent protection? Yes, either a fuse or a circuit breaker can be used for overcurrent protection as long as it meets the NEC requirements and is properly sized for the application. Where should I locate the overcurrent protection device for the generator? The overcurrent protection device for the generator should be located in the generator's control panel, as close as possible to the generator output terminals. What happens if the overcurrent protection device trips? If the overcurrent protection device trips, it indicates that there is an overload or short circuit condition in the circuit. You should investigate the cause of the trip and correct the problem before resetting the overcurrent protection device. Is it necessary to ground the transfer switch? Yes, the transfer switch must be properly grounded in accordance with the NEC requirements. Grounding provides a path for fault current to flow back to the source, which helps to trip the overcurrent protection device and prevent electrical shock hazards. Can I install the transfer switch myself? It's generally not recommended to install a transfer switch yourself unless you have extensive electrical experience and knowledge of the NEC. Electrical work can be dangerous, and it's best to leave it to a qualified electrician. Finally, let's consider the impact of different types of transfer switches on overcurrent protection requirements. There are two main types of transfer switches: manual and automatic. A manual transfer switch requires the user to manually switch between the utility grid and the generator. An automatic transfer switch automatically switches between the two sources when it detects a power outage. The overcurrent protection requirements are generally the same for both types of transfer switches. However, automatic transfer switches may have additional features, such as automatic voltage regulation and frequency control, which can affect the performance of the overcurrent protection devices. In summary, understanding the NEC requirements for overcurrent protection with transfer switches is crucial for ensuring the safety and reliability of electrical installations. By following the code and consulting with a qualified electrician, you can minimize the risk of electrical hazards and ensure that your electrical system operates properly. Remember to always prioritize safety when working with electricity and to seek professional assistance when needed. The information provided here is for educational purposes only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician before performing any electrical work. Let's explore some additional considerations for transfer switch installations, particularly focusing on specific scenarios and potential challenges. In situations where the generator is located a significant distance from the transfer switch, it's essential to consider the voltage drop in the conductors between the generator and the transfer switch. Voltage drop occurs when the voltage at the load end of the conductor is lower than the voltage at the source end. Excessive voltage drop can cause equipment to malfunction and can also damage conductors. To minimize voltage drop, it's necessary to use conductors of adequate size. The NEC provides tables that specify the allowable voltage drop for different types of circuits. It's also important to consider the ambient temperature when selecting conductors. The ampacity of a conductor decreases as the ambient temperature increases. Therefore, it's necessary to select conductors with a higher ampacity rating if they are installed in a high-temperature environment. Another important consideration is the coordination of overcurrent protection devices. Coordination refers to the selection and arrangement of overcurrent protection devices so that the device closest to the fault will trip first, minimizing the impact on the rest of the electrical system. Poor coordination can result in unnecessary outages and can also damage equipment. To achieve proper coordination, it's necessary to consider the time current characteristics of the overcurrent protection devices. The time current characteristic is a graph that shows the amount of time it takes for a device to trip at different current levels. By comparing the time current characteristics of different devices, it's possible to select devices that will coordinate properly. In some cases, it may be necessary to use fuses with different time delay characteristics to achieve proper coordination. Time delay fuses are designed to withstand temporary overloads without tripping, allowing downstream devices to clear faults first. When installing a transfer switch in a commercial or industrial setting, it's important to consider the requirements of the local utility company. The utility company may have specific requirements for the type of transfer switch that can be used, as well as the overcurrent protection and grounding requirements. It's also important to coordinate the installation with the utility company to ensure that the transfer switch is properly connected to the utility grid. In areas that are prone to power outages, it's becoming increasingly common to install automatic transfer switches with energy storage systems such as batteries or flywheels. These systems can provide backup power for a limited time, allowing critical loads to continue operating during a power outage. When installing a transfer switch with an energy storage system, it's important to consider the charging and discharging characteristics of the energy storage system. The transfer switch must be able to properly manage the flow of power between the utility grid, the generator, and the energy storage system. It's also important to provide adequate overcurrent protection for the energy storage system. Another emerging trend in transfer switch technology is the use of solid-state transfer switches. Solid-state transfer switches use electronic components, such as silicon-controlled rectifiers or insulated gate bipolar transistors, to switch between power sources. Solid-state transfer switches offer several advantages over traditional electromechanical transfer switches, including faster switching speeds, higher reliability, and reduced maintenance requirements. However, solid-state transfer switches also have some limitations, such as higher cost and sensitivity to voltage transients. When installing a solid-state transfer switch, it's important to follow the manufacturer's instructions carefully and to provide adequate surge protection to protect the electronic components. Finally, let's address some common misconceptions about transfer switches and overcurrent protection. One common misconception is that a transfer switch is only necessary if you have a generator. While a transfer switch is often used with a generator, it can also be used to switch between other power sources, such as a solar panel system or a wind turbine. Another misconception is that the overcurrent protection device in the generator will protect the entire electrical system. The overcurrent protection device in the generator only protects the generator itself. The electrical system must have its own overcurrent protection devices, sized according to the load requirements. A further misconception is that all transfer switches are created equal. There are different types of transfer switches available, each with its own features and limitations. It's important to select a transfer switch that is appropriate for the specific application. And lastly, it's a mistake to think that you can install a transfer switch without any electrical knowledge. Electrical work can be dangerous, and it's important to have a thorough understanding of the NEC and electrical safety practices before attempting to install a transfer switch. In conclusion, transfer switches are essential components of electrical systems that provide a reliable means of switching between power sources. By understanding the NEC requirements for overcurrent protection and following proper installation practices, you can ensure the safety and reliability of your electrical system. Remember to always consult with a qualified electrician before performing any electrical work.